Hello, everyone. Can you hear me? All right, perfect. So my name is Muammar Mansor. I'm a graduate student from Penn State University, and I'm going to talk about molybdenum and nitrogen co-limitation to ecosystems in the Proterozoic ocean. And so, as astrobiologists, we are interested in finding life in the universe. One of the places that we have identified to harbor life might be Earth-like planets. But when we think of Earth-like planets, what type of life forms do we expect to find there? Do we expect to find simple life that can perhaps evolve to complex life and to intelligent life? Is this evolutionary transition inevitable? Well, some suggest that there are barriers that will prevent this evolution. And in order to start answering this question, we can look towards Earth history as a case study. The Earth, over a period of 4.5 billion years, have undergone dramatic changes from a possibly iron-rich ocean in the Archean to a sulfidic ocean in the Proterozoic and to an oxygen-rich Earth in the world that we live in today. And it was thought that the earliest microbes arose pretty early on, around 4 billion years ago. This followed a period of where major eukaryotic diversification happens around 500 million years ago. And there seems to be a long period, about 4 billion years, where it took from simple life to complex life. And then finally, intelligent life arose pretty rapidly after the major eukaryotic diversification. And so my project involved looking at this long period of seemingly evolutionary stasis from microbes to eukaryotes transition. What are the barriers that prevent this transition happening earlier on in Earth history? And so one idea that was proposed by, as far as I know, in 2002 by Ariel Anbar and Andrew No, is that there were molybdenum and nitrogen co-limitation to Proterozoic ecosystem. And so in order to understand this hypothesis, we must first understand the molybdenum cycling in the modern ocean. Today, molybdenum is supplied primarily through oxidative weathering of continents to the modern ocean with concentrations of about 100 nanomolar. Molybdenum is also removed from the ocean with its primary sinks being sulfidic regions. And because the Earth has undergone dramatic geochemical changes throughout history, and because molybdenum is supplied through oxidative weathering, it is thought that the molybdenum concentrations on the ocean will change as a function of oxygen concentration. So here we can see the oxygen evolution, where it increased after the Great Oxidation event, and then followed after by a second oxidation event. Molybdenum concentrations are also thought to change over time, being pretty low in the Archean, and then increasing slightly in the Proterozoic, and finally increasing by a lot during the Phanerozoic. Molybdenum, as it turns out, is a pretty important cofactor in nitrogen fixing enzymes such as nitrogenase. And here we can superimpose an experimental nitrogen fixation limit through laboratory cultures. And here, so below this period, molybdenum is limiting to nitrogen fixation, and thus there potentially a lack of nutrients to support the transition to a eukaryotic world. And so the questions here, so through biogeochemical modeling, people have suggested that molybdenum concentrations are about 1 nanomolar in the Archean, and then it increased to about 10 nanomolar in the Proterozoic. But especially in the Proterozoic, there are huge uncertainties with molybdenum concentrations because we don't know whether the ocean was really sulfide-rich and how much of the ocean was subjected to sulfidic conditions. And so one proxy that has been suggested to be useful in order to reconstruct seawater molybdenum throughout time is the molybdenum content in pyrite. Pyrite is an iron disulfide mineral. During its precipitation, molybdenum in seawater can be incorporated into pyrite crystal structure as impurities. And this has been suggested by Ross Large and others that it can be used as a proxy for seawater molybdenum concentration. Ross Large and others produced a data set where the molybdenum content of pyrite, they analyzed molybdenum content of pyrite through laser ablation and shown it as a function of time. And we can see that in terms of relative amount, there's very low molybdenum content in pyrite in the Archean, with a slight increase in the Proterozoic, and finally a huge increase in the Phanerozoic. However, there is no quantitative constraints on these values. Currently, we are only considering them as relative. And so what I wanted to do is to do experiments in order to derive a relationship between the molybdenum content of pyrite and actual molybdenum concentrations in the water so that we can get quantitative constraints that we can compare to actual biological limit. And so we set out to do this in the laboratory and to grow pyrite under controlled experimental conditions. So we precipitated pyrite in these reactors that contain a baseline of 10 nanomolar molybdenum as in the form of molybdate ion. We added iron and sulfide together. We tested several different conditions, variable initial dissolved molybdenum, as well as the effects of precipitation rate and pH to molybdenum content in pyrite. Pyrite was separated from the reactors using a sequential acid extraction, and we measured the molybdenum content in pyrite using ICP-MS. In our baseline condition, where we only added ferrous iron and sodium sulfide at pH 7, we found that the reaction was very slow, and it never reached completion. So we modified the baseline condition by adding elemental sulfur. And by adding elemental sulfur, we actually increased the precipitation rate for pyrite. We also, the reaction progressed to completion. We can also test different molybdenum concentrations now. So we tested concentrations between 10 to about 10,000 nanomolar molybdenum. We also tested different pH. So all of these experiments were done at pH 7, and these were done at pH 9. Interestingly, we found that pH causes an effect to precipitation rate. So there was slower precipitation at pH 9 relative to comparable condition at pH 7. We also found out that when we added high amounts of molybdenum to experiments at pH 9, molybdenum precipitates out in a mineral phase that was not associated with pyrite. So we didn't consider this data in our study, in our interpretation. The preliminary results were very encouraging in that we found that the molybdenum content in pyrite correlates very well with the initial dissolved molybdenum concentration in our reactors. We get an R-square value of 0.83. We did not find any significant difference with either precipitation rate or between different pH or between different amounts of elemental sulfur. We do see this huge scatter, which seems to be correlated with the amount of pyrite that we make in our reactors. So as we make more pyrite, we decrease the molybdenum content in pyrite, or the molybdenum over iron ratio in pyrite. So now that we have this interesting correlation to experimental conditions, we wanted to see whether we can apply this, whether we can actually use this in natural system. So this is the same plot as before, molybdenum content in pyrite versus concentrations, and this is the experimental line. And so we want to compare this with modern pyrite, where we have data of their molybdenum content as well as the molybdenum concentration in the water above them. Pyrite is one of those complex minerals that can form under a variety of conditions. So the first one that we looked at was diagenetic pyrite that forms under oxic to suboxic water columns. These pyrite are formed in sediments, and they fall right somewhere along this line. We also look at syngenetic pyrite, pyrite that was formed in the water column. So this pyrite, in this water column, there can be stratification with surface water that contains high molybdenum content, and a sulfidic bottom water that contains lower molybdenum concentration. And so that's the reason for this line here. This is from the Black Sea, where the concentration of the water can vary between the bottom and the surface water. We also look at biofilm-associated pyrite. Today, this mode of formation of pyrite is rare, but it could have been more important on the early Earth. So a few things pop out here. The first one being that the experimental relationship kind of works for diagenetic pyrite, but we can see that there's clear overestimation. There's a clear bias towards higher value, especially for syngenetic and biofilm-associated pyrite. So we cannot use this experimental line directly. We have to account for these complication factors in order to reconstruct seawater molybdenum over Earth's history. And so we propose a couple of strategies in order to reconstruct seawater molybdenum. So this is the molybdenum content. This is the data of molybdenum content in pyrite collected through laser ablations, compiled from literature. Blue are pyrite from black shales, while orange are from shallow microbial carbonates. And we have, as you notice here, we have put the molybdenum concentration data on the axis on the right. And so if we use the data directly, molybdenum concentrations in the modern ocean can predicted to be as high as 10,000 nanomolar, which doesn't seem to be accurate at all. There is no place that currently has 10,000 nanomolar molybdenum. But one way we can try to remove this bias towards higher value is to remove the data from syngenetic pyrite, which can be identified through the use of several geochemical proxies, one of them being the degree of pyritization. Another thing that we did was to use the median as the upper limit instead of the maximum, and to use the minimum as the lower limit. So we can put constraints in order to try to reduce the bias towards higher values. And so this is what we did. So this is the median for the black shales, followed by the minimum, and we can collapse this data in order to get some constraints on seawater molybdenum over time. We can do the same thing for carbonates, and we get this trend for seawater molybdenum over time based on black shales and carbonates. And so if you look here, the data is pretty interesting in that so we can also superimpose the nitrogen fixation limit, which is about 5 nanomolar around here. And so as you can see, the data from the Archean suggests that molybdenum concentrations were below the nitrogen fixation limit as predicted by biogeochemical models. And in the modern ocean, the value is somewhere between 50 to 100 nanomolar. So that gave me some confidence that this approach might work. And then we can compare the data to what happens in the Proterozoic. So we get a value of between 5 to 50 nanomolar with an average value of 20 nanomolar molybdenum. And so based on this simple reconstruction, it seems that seawater molybdenum concentration in the Proterozoic is above the nitrogen fixation limit. And so it may not be the barrier for eukaryotic evolution during this time period. But of course, we have to use the data with caution. There's clear overestimation from syngenetic and biofilm pyrite, which we haven't fully removed because we lack geochemical proxies data to identify either both of this type of pyrite. So perhaps uranium isotopes can help us with some of that, and some other redox-sensitive isotopes. And so in summary, we were wondering if molybdenum and nitrogen co-limitation can act as a barrier to eukaryotic diversification. We have conducted experiments in the laboratory that shows that the molybdenum content in pyrite correlates very well with dissolved molybdenum concentrations. We used the experimentally derived line in order to reconstruct seawater molybdenum and show that the molybdenum concentration in the Proterozoic is potentially not limiting nitrogen fixation and may not be the barrier for eukaryotic diversification. And finally, we need more development of proxies in order to identify syngenetic pyrite and biofilm-associated pyrite so that we can use this technique more effectively. Thank you.
All right, thanks very much. We have time for a quick question or two while we switch over.
You show very low molybdenum concentrations for archeal. A lot of very important enzymes are using molybdenum. There was life in archeal time. How you explain that? How they were coping with?
So there are other, nitrogenase, for example, can have other different cofactors. Molybdenum is not the only cofactors. It is certainly the most efficient form, but iron, for example, can be substituted in place of molybdenum.
But another question, the terrestrial volcanic systems that are producing a lot of molybdenum.
Okay.
Probably, do you consider this molybdenum delivery in your calculations, or you just consider the ocean samples?
So in this respect, pyrite is a proxy for seawater. So we only consider the oceanic system, but not terrestrial. But that's one good point.
Thank you.
Yep.
It's a very interesting talk. So my question is, does molybdenum actually sit in the lattice of the pyrite, or the molybdenum actually present some negative and they're just trapped by the pyrite?
So I think this is still an area of ongoing research, but the current consensus is that it is a nano inclusion in pyrite.
Okay.
Yep.
All right, thanks.
We have time for one more?
Sure,
Okay.
real quick. Sure.
That was a great talk. Thanks.
Thank you.
So honestly, I kind of have a comment just to update update the field with some unpublished research, because it's interesting to me that this all kind of hinges around this 5 nanomolar number that
Yep.
Ariel's group, when I was a PhD student, and also Aubrey Zirkle came up with. But now that we've been doing more field research, it's pretty hard to find molybdenum-limited environments, and I think some people have found them, but they're pretty rare. And most freshwaters have, we're talking, sub-nanomolar levels. And so I just want to I think there's a kind of caveat that they're not using, so far we've not found an environment that's using an alternative nitrogenase. So based on the modern, we don't have evidence that alternative nitrogenase is important everywhere. So just when thinking about that vanadium question, I think it's important to kind of constrain it with some modern environment. So I'm happy to talk more.
Yeah, I agree with that. There's a lot of research going into is there an actual threshold or not. Yeah.
Cool.
Okay.
All right,
Thank you.
thank you.